Welcome to ReakInfo, where we dive into chemistry, moving from the basics to advanced concepts for clarity and influence. This video is focused on mole concept mastery, which is essential to build a strong foundation in numerical chemistry. The mole concept is the backbone that connects all numerical problems in chemistry. Mastering it unlocks success across multiple concepts, including stoichiometry, thermodynamics, electrochemistry, and organic numericals. If you master this, half of chemistry becomes structured and predictable. So what is a mole? 1 mole equals 6.022 times 10 to the power of 23 particles. Think of it as chemistry's counting unit, connecting the atomic scale to measurable laboratory quantities. This conversion flow map illustrates the pathway for solving most numerical problems. You can convert between mass, moles, particles, and for gases, gas volume at STP. The core formulas are the backbone of mole concept calculations. They include equations for number of moles and particle count. And for gases at STP, 1 mole occupies 22.4 liters. Here is a quick example. To find moles in 44 grams of CO2, first calculate the molar mass, which is 44 grams per mole. Then, apply the formula to find that it equals 1 mole. It's simple, structured, and logical, right? Now comes the most important application, limiting reagent. The limiting reagent concept is key, as it determines how much product forms in a chemical reaction. The limiting reagent is the reactant that is completely consumed first, and thus determines the maximum yield of the product. The golden method involves 3 steps: convert to moles, divide by coefficient, and identify smaller value. That smaller value controls the reaction and shows you the limiting reagent. In this worked example for a limiting reagent problem, after dividing by coefficients, we find that aluminum is the limiting reagent, and using it, we calculate the mass of iron formed, that is 56 grams. When dealing with gas mixture and stoichiometry problems, follow the same 3 steps: convert to moles, divide by coefficient, and determine the result. For this example, the mass of water formed is 36 grams. If the divided values are equal, the mixture is perfectly stoichiometric. No reactant remains in excess. Now let's handle impurity problems. Impurity and limiting reagent problems require finding the pure mass first. Then, proceed with mole conversions and ratio calculations to find the final volume of CO2 at STP, which is 1.792 liters. Thus, structured steps eliminate all confusions. Advanced back calculation problems involve working backward from the product. Sometimes you're given product volume and asked to find reactant mass. To find the mass of magnesium required, first find the moles of H2, then use the stoichiometric ratio, resulting in 6 grams of magnesium. For mixed concepts involving limiting and leftover reactants, identify the limiting reagent by dividing by the coefficient. Then, calculate the leftover amount of the excess reactant. Here, 1 mole of H2 is leftover. Balance and comparison are key here. Now let's explore empirical and molecular formula. Assume 100 grams, use the given data, and convert percentages to moles. Next, find the mole ratio of elements to determine the empirical formula, and then use molar mass to determine molecular formula. The gas density concept uses the key concept that 1 mole occupies 22.4 liters at STP. The formula for molar mass is density multiplied by 22.4. On direct application of this formula, we get the molar mass as 28 grams per mole. This multi-step reaction problem involves calculating the mass of water formed and the mass of leftover reactant. The steps show it is an exact stoichiometric mixture, resulting in 36 grams of H2O formed and no leftover reactant. For volume-volume reactions, the limiting reagent concept applies to volumes under the same conditions, because gases at same temperature and pressure follow mole ratio. Here, carbon monoxide determines the reaction extent, and 10 liters of CO2 are formed. This combined problem, integrating gas purity and stoichiometry, follows a 5-step process, from calculating the pure mass, followed by number of moles and mole ratio. This ratio helps to find the final volume of H2 at STP, which is 1.55 liters. Always, stick to this structure. Pure mass leads to moles, moles to ratio, then final quantity. Consistency builds mastery. To recap, remember the mole is a counting unit. Always convert to moles first. Divide by the coefficient for the limiting reagent. and adjust for purity in real-world applications. Practice consistently to structure your chemistry knowledge. Thanks for watching. If this session helped you build clarity, subscribe to my channel. See you in the next session. Bye.